Good evening, children.
Good evening, ma'am.
Good evening. So, Raja, you're back from the tour, huh?
Yes, ma'am. Just
Very
yesterday
good.
morning.
Oh, very nice. Okay. All right, children. So, this is the first question I shared as a part of the pre-work. All of you have completed? All the three?
Yes, ma'am.
All right. Very good. Okay. So, here in a circle of radius 21 centimeters, an arc subtends an angle of 60 degrees at the center. In a circle of radius 20 centimeters, an arc, say arc AB, an arc, say arc AB, subtends an angle of 60 degrees at the center, center O. So this arc subtends. So how do you show the figure? You need to join the ends of the arc to the center of the circle. To represent this in the figure, that the arc subtends an angle of 60 degrees at the center, you need to join the ends of the arc to the center of the circle. So one end of the arc is A, join that to the center of the circle. The other end of the arc is B, join that to the center of the circle. So this is the angle subtended by arc AB at the center O, and this is 60 degrees. Now,
Ma'am, are you
we need...
sharing the screen?
Oh, thank you so much. No, goodness. Sorry, and thank you, Rakshita. Yeah. Yeah, it should be visible now, right?
Yes, ma'am.
Yeah, okay. So I'll have to come from the beginning. Circle, center O, arc AB, join the ends of the arc. The ends of the arc are A and B. Join them to the center of the circle. So join A to O and B to O. Now this is the angle subtended by arc AB at the center, which is given to be 60 degrees. Now with this information, we have to find the length of the arc. So length of arc means length of this arc, because this arc subtends 60 degrees at the center. We need to find the length of this arc. Now we know that the length of this arc, or this arc, is a part of the circumference of the circle. So its length will be some fraction of 2 pi r. And so the formula, length of arc AB is equal to theta by 360 into 2 pi r. Into 2 pi r. We understood this in the last class. So this will give you the length of arc. Then the area of the sector formed by the arc. Theta by 360, this fraction of 2 pi r, will give you the length of arc AB. Area of the sector. Now, this is the sector. To find the area of the sector, so this sector is a part of the area of the circle. It's a part of the circle. So its area will be a part of the value of the area of the circle. So what part? So we need to find that fraction. So again, theta by 360. Theta by 360 into pi r square. Pi r square is the area of the circle. The sector occupies some part of the area of the circle pi r square. So what part, what fraction? Theta by 360. So 60 by 360 into pi r square, where r is 21. Next, we have to find the area of the segment formed by the corresponding chord. Okay, the corresponding chord is the chord which is present in this sector. This is the corresponding chord. Corresponding chord is got by joining the ends of the arc. A and B are the ends of the arc. A and B are the ends of the arc. Join. So you get the line segment AB. And what do you call this line segment AB? It's a chord to the circle. Area of the segment formed by the corresponding chord. The arc is AB. A and B are the ends of the arc. Join the points A and B. So you get a line segment, and this line segment is the chord to the circle, or it's a chord in the corresponding sector, or the chord made by the corresponding arc. So we need to find the area of the segment. So this one, this is the area of the segment. This one, we need to find this area. So we understood that the area of the sector is made up of area of triangle and the area of the segment. The area of the triangle and the area of the segment together make the area of the sector. So from the area of the sector, if you take away the area of the triangle, you will get the area of the corresponding segment. So this is the sector OAB. OAB, sector OAB. This is the corresponding chord. So you can see a triangle OAB and the segment here. We need to find the area of the segment. So area of the segment is area of the sector minus the area of the triangle. And it's an equilateral triangle because the angle is 60 degrees. So this one is an equilateral triangle. You can find its area using the formula √3/4 a square. Area of sector we have already found. Minus the area of the equilateral triangle will give you the area of the segment. Understood this working, children? Any questions here?
No, ma'am.
Okay. Others?
No, ma'am.
Sashant is representing the class. Madhumita. Next, others? Any questions?
No.
Okay. I don't remember the questions I shared. I shared 160 degrees, 190 and 120. Oh, I shared the sixth one, is it? I think I explained the fifth one. It's okay. I didn't share the fifth one. Okay, I've shared 4, 7, and 6. Okay. Okay, anyways, I've explained 5, but I've shared 4, 6, and 7, not 5. Okay, let me go to the fourth one now. Yeah. Okay, so in this question, the radius is 15. Similar situation, radius is 15. We need to find the areas of the corresponding minor and major segments. We need to find the area of the corresponding major and minor segments. So circle, chord, arc AB, center, angle subtended at the center is 60 degrees. So we need to find the area of this segment, which is the minor segment, and the area of this segment, which is the major segment. This one, which is the major segment. This is the minor segment. This is the minor segment. This one is the minor segment. The rest of it is the major segment. Segment is a region bounded by a chord and an arc. Chord and an arc. Chord and an arc. Okay. So we understood how to find the area of the segment. We just understood that. Find the area of the sector. Find the area of the sector. Then the area of the triangle. Area of the sector minus the area of the triangle is the area of the segment. Now, the area of the circle minus the area of the minor segment will give you the area of the major segment. So to find the area of the segment, you have to find the area of the sector, the corresponding sector. So area of sector, area of triangle. The difference will give you the area of the minor segment. Then the area of the circle minus the area of the minor segment will give you the area of the major segment. A lot of number work, children. You'll have to be very careful while calculating. There'll be a lot of number work in this chapter, volumes and surface areas. And pi, you must take 3.14 if mentioned. Otherwise, it's always 22/7. So here also, question is the same, meaning similar situation, the angle and the radius are different. Radius 10 centimeters and angle is a right angle. So that makes the triangle a right triangle and whose area is found using the formula half base into height. Half into base into height. It's a right triangle. So we find the area of the right triangle using the formula half base into height. Half into OA into OB. The sides containing the right angle are regarded as the base and height. So here also area of minor segment, major segment. So you need to find the area of the sector, then the area of the triangle. It's a right triangle, half base into height area. The difference between these two will give you the area of the minor segment. Then the area of the circle minus the area of the minor segment will give you the area of the major segment. Oh, sorry, this is major sector. Huh? Okay. We have to find the area of the correspond. I'm just assuming the questions. Sorry. Minor segment, I said minor sector, triangle, difference will give you the area of the minor segment. Then major sector, we need to find the area of the major sector. How does a major sector look like? See here. This is the major sector. This is the major sector. Here is a 9. Here is that right angle. This area is the major sector. A sector is a region bounded by 2 radii and an arc. Major sector, so major arc. Minor sector, minor arc. We need to find the area of the major sector. Major sector, which is that major sector? Minor sector is this one. Minor sector is this one, the one which contains a right angle. This one is the minor sector. This piece is the minor sector, which is the major sector. Here we have 90 degrees, 2 radii and an arc, the major arc. The major arc. This one is the major sector. We need to find the area of this region. So what is the major sector angle? Major sector angle. This angle. 360 minus 90. 360 minus 90. Okay. So 360 minus 90 is 270. So you can find it like this. 270 by 360 into pi r square. Or you can also do find pi r square and subtract the area of the minor sector to get the area of the major sector. You can either find it directly. You can do this in 2 ways. You can find it directly using the formula 270 by 360 because this angle is 90. So the major sector angle will be 360 minus 90, 270. So 270 by 360 into pi r square because a sector, the sector area is a part of the area of the circle. Sector area is a part of the area of the circle. The area of the circle is pi r square. So this is some fraction of pi r square and that fraction is 270 by 360 of pi r square into pi r square. So this will give you the answer directly. Or you can also find pi r square, that is the area of the circle, and subtract the area of the minor sector. Take away the area of the minor sector. You will get the area of the major sector. Because the minor sector and the major sector together form the area of the circle. So I think that's what I've done here. I found the area of the circle and then area of the circle minus the area of the minor sector, children, not segment. Area of the major sector will be area of the circle. So 4, where is 4? This one, area of the circle, minus the area of the minor sector, this one, 1, 4 minus 1. Oh, by mistake, I've written 3, I think here. It's not 3, it's 1. It's not 3, children, it's 1. I don't know if you noticed it. It's not 3 children, it's 1. So from the area of the circle, this is the area of the circle, 4 is the area of the circle, and 1 is the area of the minor sector. The difference will give you the area of the major sector. I tell you again, this one is the major sector. So from the area of the circle, take away this area, subtract this area. This is the minor sector area to get the area of the major sector. I've taken 78.5, but by mistake, I shouldn't have done that mistake. Yeah, it's not 3, it's 1. Yeah, any questions, children? If it is not clear, segment, sector, if you're getting confused, please ask me now. Okay. Next is when the sector angle is 120 degrees. The radius is 12 centimeters. Sector angle is 120 degrees. Find the areas of the corresponding segment of the circle. Find the area of the corresponding segment of the circle. So 120 degrees, the segment present in the sector, whose sector angle is 120 degrees. You should find the area of that segment. Circle, center of the circle, 120 degrees, arc AB, center O, any point C, and this is the chord. This is the chord. The radius is 12. Radius is 12. Sector angle 120 degrees. ACB is the arc. Arc ACB subtends angle AOB at the center. And angle AOB is equal to 120 degrees. Arc ACB subtends 120 degrees at the center. And 120 is less than 180. 120 is less than 180. So the arc is a minor arc. Minor arc. If the angle subtended at the center is more than 180, then the arc will be a major arc. If the angle subtended at the center is less than 180 degrees, then the arc is a minor arc. If the angle is more than 180 degrees, if the arc subtends an angle greater than 180 degrees at the center, then that arc is a major arc. So ACB clearly is a minor arc because it subtends 120 degrees at the center, which is less than 180. So the corresponding sector formed is a minor sector. Minor arc, minor sector, minor segment. ACB is the minor arc. And this one is the minor segment. This one is the minor segment. And the whole thing, this whole thing, that is OACB. OACB is the minor sector. OACB is the minor sector. But we need to find the area of the corresponding segment, that is this segment, this one. So first we need to find the area of the sector, 120 by 360 into 120 by 360 into pi r square. Because again, area of the sector is a part of the area of the circle. So 120 by 360 is a fraction. It's 1/3. This sector occupies 1/3 the area of the circle. So this is first step. Next is to find the area of the triangle. So the sector angle is 120 degrees. So the area of the triangle is r square sine theta by 2. Sine theta by 2. Theta by 2 is 120 by 2. Sine 60 degrees. Cos theta by 2. 120 by 2. 60 degrees. So r square, 12 square, 12 into 12, 144 into sine 60, root 3 by 2. cos 60, 1 by 2. So find this value. This will be the area of the triangle. Then the area of the segment will be 1 minus 2. 1 minus 2. The answer you get in 1 minus the answer you get in 2. All right. All right, children, let's proceed now. Now this exercise is deleted from the syllabus. Now, Sashank and Madhumita, you have learned this chapter at school, so you can just tell us something. Have you, if you have the old NCERT textbook, then you will find this exercise. Has this been done in school?
No, ma'am. Yes, ma'am.
Yeah, so that this becomes a part of the extra problems now. This becomes a part, this was a part of NCERT until last year. Now it's not an NCERT, it's removed from the textbook, but now it becomes a part of the extra problems.
Ma'am, it was not taught for us, ma'am.
Yeah, no, but anyways, we have to go beyond the syllabus, meaning beyond NCERT, to prepare for the exam. So we need to have all this. We need to learn how to, work such situations also.
Yes, ma'am.
Yeah. Now here in this question, in the figure, two circular flower beds. Two circular flower beds. Circular flower beds meaning they are a part of a circle. The flower beds are a part of the circle, are a part of a circle. Two circular flower beds. You will not find the circle here, but the flower beds are a part of a circle. Two circular flower beds have been shown on two sides of the square lawn ABCD of side 56 meters. So they're talking about this square lawn. They're talking about this square lawn ABCD. Okay. And on two sides, that is on the side AB and CD, as you can see there in the figure, on the two sides AB and CD, you can see the circular flower beds. Circular flower beds, you can only see an arc like this. You can see only this arc here and this arc here. But it's a part of a circle, like you can complete it and it's a part of a circle. This one is a part of a circle. That's what is meant by circular flower beds here. So ABCD is the square of side 56 meters. On the sides AB and CD, we see two circular flower beds. If the center of each circular flower bed is the point of intersection O of the diagonals of the square lawn. Okay, so AC and BD are the diagonals of the square lawn. AC and BD are the diagonals of the square lawn. And it's given the point of intersection is O. So this is O. Now it's given that O is the center of each of the circular flower beds, because if it's a part of a circle, then there should that circle of which the flower beds are a part will have a center. The circle of which the flower beds are a part will have a center. So this is the center of each of the circular flower beds. Okay, so this is the center of each of the circular flower beds. If the center of each circular flower bed is the point of intersection O of the diagonals of the square lawn, find the sum of the areas. Find the sum of the areas of the lawn and the flower beds. So that's the question. we need to find the sum of the areas. You don't have to find it separately. Find the sum of the areas. That is, we have two things here. We have one square lawn and then the circular flower beds. We need to find this total area. We need to find the total area. This is the square lawn. This is the square lawn. And these are the circular flower beds. Find the entire area. That's the question. Find the sum of the areas of the lawn and the flower beds. Okay. Now you can look at this figure in 2 or 3 different ways. So let's see the first one now. Now, using the properties of a square, the diagonals of a square are equal. They bisect each other at right angles. The diagonals of a square are equal. They bisect each other at right angles. So this angle is 90 degrees, meaning everywhere it is 90. Angle AOB is 90, AOD is 90, DOC, BOC, everywhere it's 90 degrees. Around the point O, there are 4 angles. Each of the 4 angles measure 90 degrees. By the property, diagonals bisected right angles in a square. Diagonals are equal in a square. All right. So now look at this one. This is the center. This is the center. This is the circular flower bed. Circular flower bed. So this is the circumference, right? Now with this point A and B, and you can see BO, AO, and the angle is 90 degrees here. So this is a sector then. This one together, this one and this one together is a sector. Is a sector. You can look at AB as arc AB, subtending 90 degrees at the center because it's given that O is a center. So arc AB subtends 90 degrees at the center. So this one is a sector with sector angle 90 degrees. Sector because you can see radius, and arc. Now, if the question is how do we regard OA and OB as a radius? Yeah, because if AB is the arc, then A and B are the points on the circumference. Arc is a part of the circumference, then A and B are points on the circumference. So any line segment joining the center to a point on the circumference is the radius. Any line segment connecting the center of the circle to any point on the circumference is the radius. And hence OA, OB are the radii of the circle. Similarly, the same thing holds good for this one. This one is also a sector. So you can look at this whole figure as 2 sectors and 2 triangles. One right triangle here and one right triangle here. Right triangle here, right triangle here. So that's the first approach. We're looking at the whole figure as 2 sectors. One sector here like this. Another sector here like this. And one triangle here. A triangle here. This one is a triangle. And this one is a triangle. This one is a triangle. So this is the whole figure. And it's a right triangle because this is 90 degrees. Everywhere it's 90, no? So they're right triangles. Okay, so we've got the outline as to how to proceed. So we know that we have to find the area of one sector multiplied by 2. Area of one triangle multiplied by 2 because they're similar. Not similar, they're equal, meaning they're congruent. Not similar, they're congruent. The 2 sectors are congruent. The 2 triangles are also congruent. They're identical. They're identical. So you can find the area of one sector, multiply, double it. Find the area of one triangle, double it, and add to find the area of the whole figure. So now when we say circular flower beds, for anything circular, we need only one value, which is the radius. For anything circular, you need only one value, which is the radius. If you have the radius, you can answer any question. And for a triangle, it depends on what formula you have to use. So this is a right triangle. So half base into height. So you need the base and height to find the area of this triangle. So now let's start with finding the radius of the circular flower beds. OA and OB are the radius, or the OA and OB, they are the radii of the circular flower bed. Now OA is a part of the diagonal AC. OA is a part of the diagonal AC, or OB is a part of the diagonal BD. So we need to find OA, which is half of AC. We need to find OA or OB, which are half of AC or half of BD, respectively. So we need to find AC. And how do you find AC? We have only one numerical value here, which is the side of the square. We only know that the side of the square is 56 meters. So we need to get started from here. Okay, this is 56, this is 50, all over 56 it is. So we need to find the radius. You can use the formula. I don't know if I've used, yeah, I've used the formula. So you can use the formula. You can use the Pythagoras theorem to find the length of the diagonal, or you can straight away use the formula root 2a. Root 2a. Root 2a is the formula to find the length of the diagonal of a square. Use this. A stands for the side of the square. So root 2 into 56. 56 root 2. Root 2 into 56, or 56 root 2 will give you the length of the diagonal. Divide that by 2. So 28 root 2. 28 root 2. So you can see here. Yeah. So this is the first step. Diagonal root 2a, 56 root 2. Then the OA, OB, OC, OD, whatever will be 28 root 2. 28 root 2. So now we found the radius. We found the radius. Next is to check if we have the base and height for the triangle. Base and height for the triangle. Okay. So the sides containing, whenever it's a right triangle, the sides containing the right angle are taken as the base and height. So OD is the base, AO is the height. Yeah, that we have, no? That's a radius only. That we already have. Base and height we have, because OD is the base, AO is the height. Yeah, we have it, 28 root 2. So that also we can find half base and height. Half 28 root 2 into 28 root 2 will give us the area of the triangle. So that's it. So half base into height will give us the area of the triangle. Understand, children?
Yes, ma'am.
Why no response from the others? Class, use emoji, raise your hand. Rashmi, Madhumita, Prajit, Raja, Danya, Florentina, Ranjan, Arjun, Sishant, and Rakshita. Rakshita, you there? Yeah, she's there. Okay. Okay. Yeah. All right, children. So you need to just first plan before you, because you cannot simply start working something randomly. You need to first plan and then execute your plan. So before you find anything, you have to find the radius. A radius, which is OA or OB or OC or OD. So find the diagonal using the formula root 2a. Half of that will be the radius. And now how do you find the area of the sector angle is 90 degrees. The sector angle is 90 degrees. So the area of the sector will be 90 by 360 into pi r square. 90 by 360. The two sectors have a sector angle of 90 degrees. They are quadrants. If the sector angle is 90 degrees, it's a quadrant. If the sector angle is 180 degrees, it's a semicircle or a semicircular region. If the sector angle is 90 degrees, it's a quadrant. So 90 by 360 into pi r square. And then half base into height. Yeah, see here. Yeah, so finding the area of the sector AOB, 90 by 360 into pi r square. The area of the other sector, the area of the other sector, CODF. The area of the other sector, CODF is also the same thing. Then the area of the triangle AOD. Area of triangle AOD will be half into base into height, half into OA into OD. Yeah, so find the area of the triangle. The same will be the area of triangle BOC. So the area of the lawn plus the area of the flower beds. We need to find the sum of the areas. Here, yeah. Will be the sum of all these things. That is, this is the area of one sector, this is the area of the other sector, this is the area of one triangle, the other triangle. Add everything. Area of one sector, area of the other sector, area of one triangle, other triangle. Add everything, you'll get the area of the lawn and the flower beds together. The required area. The required area. You can also just write the required area. Required area is equal to, because we have not found lawn and flower beds separately. We have not found lawn and flower beds separately. So you can just write required area. Required area is equal to, add everything. We have found the area of one sector, this one, then the other sector, then area of this triangle and this triangle. So add everything to get the area of the whole figure. All right, children?
Yes, ma'am.
Yes.
Yeah, very good. All right.
Mom, do we have to write that down?
No, I'll share the images with you. No.
Okay, ma'am.
Yeah. Yeah, so here tell me read the question and tell me the radius of each circle, children. Radius of each circle.
14 by 4.
14 by 4. What's the diameter of one circle?
7.
7. Okay.
3.5
So,
radius.
correct. Because the side is 14. The side is 14. So that means the diameter of this circle plus the diameter of this circle is 14. So the diameter of this one will be 7. The diameter of this one will be 7. So that means the radius is 3.5. Radius is 3.5. Radius is 3.5. 3.5. 3.5. The side of the square is 14 centimeters. So the diameter of each circle, the diameter of each circle will be 7. So the radius of each circle is 3.5. 7 by 2 or 3.5. The question is to find the area of the shaded region. Shaded region, this one. That is the region inside the square, but outside the circles. The shaded region is the region inside the square, but outside the 4 circles. All these portions, this one. You need to find the area of the shaded region. So what's the idea? How do we find the area of the shaded region? What's the idea in words?
An area of square minus area of 4 circles.
Correct. Area of the square minus area of 4 circles. So that's easy for you. You can do that. One circle is pi r square. So 4 circles will be 4 into pi r square. And I have presented it like this. R plus R plus R plus R is equal to 14. R plus R plus R plus R is 14. So 4R is 14. So R is equal to 7 by 2. 14 by 4, 7 by 2. We'll come to this later. Yeah. We need to find the area of the shaded region, this one. Find the area of the shaded region. Yeah.
Ma'am?
Yeah.
Ma'am, I have a doubt in the previous question, ma'am. We
Sure,
don't
sure.
know. We
Yeah,
don't
yeah.
know if all the circles are equal, right, ma'am? Then
No,
how
no.
can we take that?
No, no. Only if they're all equal, they can be placed like this. You can see that one circle touches two other circles at the same time. This is possible. This kind of an arrangement is possible only when the four circles are congruent. You can see that one circle touches two other circles. Every one circle touches two other circles. Like if you take this circle, it touches this circle and this circle. If you take this circle, it touches this circle and this circle. So this is possible only when, and the whole thing is a square. This kind of an arrangement is possible only when the four circles are congruent to each other. If the circles are not congruent, supposing a big circle and a smaller one. So you understand what I'm saying? All the circles will not touch each other. They'll not touch each other. See, these are touching circles. These are all the circles are touching circles. All the circles are touching circles. They all touch each other. And they all fit into the square perfectly. One circle touches two other circles at a time, at the same time. So this kind of an arrangement is possible only when the four circles are congruent to each other. Sometimes the diagram will not be given. It will be given in words that four circles are placed in a square such that in such a way that a circle touches two other circles at the same time. Find the area of the square outside the circles. So this is what it is. Sometimes the figure will be described. Four circles, they might give congruent circles, but even if it is not given, it's understood. Four circles are placed inside a square in such a way that a circle touches two other circles at the same time. Find the area of the square outside the circles. Find the area of the square outside the circles.
Okay, ma'am.
Yeah, children. I just want the idea. How do we find the area of the shaded region? Because working part, see, you're just going to work with the formula. See, like for example, this one. Now you know the idea, how to do this. Area of the square minus the area of the four circles. So square formula, you know, side, you know. Then area of four circles, pi r square into 4. R also, you know the value of r. So now it's only calculation, number work. In the same way here, the idea is important as to how to proceed with the answer. That idea is important. Once you know that you have the formula and values, you just have to substitute and calculate. That's not a big deal. Of course, the big deal is in calculating carefully. Yeah. Tell me, children, what's the idea? How do you go about answering this question? Tell me that equation in words.
Area of semicircle minus area of triangle.
Area of semicircle minus area of triangle. Okay, how do you find the area of the triangle?
We have 90-degree, ma'am.
It's not
And
given.
the
No?
length of ma'am, angle on the semicircle is 90 degree.
Correct. Angle in a semicircle is a right angle. 9 standing. Angle in a semicircle is a right angle. That means this is the diameter. The diameter will always subtend an angle of 90 degrees on the circumference. If you take any point on the circumference, and if you join the ends of the diameter to that point, this will always be 90 degrees. The diameter will always subtend an angle of 90 degrees at any point on the circumference of the circle. So here RQ or QR is a diameter because you can see that it passes through O, the center of the circle. Since QR passes through O, it's a diameter. QR is a diameter. And you can see this point P on the circumference, QPRP. That means the diameter is subtending an angle at this point P on the circumference. And that's always 90 degrees. Angle in a semicircle is a right angle. That is, the diameter will always subtend an angle of 90 degrees at any point on the circumference of the circle. The point on the circumference is P. The diameter is QR. So when you join the ends of the diameter to that point on the circumference, when you join the end points of the diameter to that point on the circumference, so Q is an end point, join Q to P. R is again the end point of the diameter, join this angle. This angle is 90 degrees. So that means RPQ is a right angled at P. So area of the triangle is half base into height. That's why it's given. PR is given here. Half base into height. This one is 7. And PQ is given. This one is given. PQ 24. So you can find the area of the triangle using the formula half base into height. This is 7. This is 24. So half base into height will give you the area of the triangle. And now how do you find for the circle you need the radius, right? The radius is not given. How do you find the radius, children?
By Pythagorean theorem, we can find the radius.
Correct. So you can find the hypotenuse QR because this one is a right triangle. The diameter becomes a hypotenuse. The diameter is a hypotenuse. So you can find QR using Pythagoras theorem. This one is given 7. This one is also given 24. This one is 24. And this is 90 degrees because the angle in a semicircle is a right angle. So area of this triangle is half base into height, half into 7 into 24. Now the idea to find the area of the shaded region is area of the semicircle. See, this one is a semicircle. This one is a semicircle. Area of the semicircle minus from this one, if you take away the area of the triangle, you will get the area of the shaded region. From the area of the semicircle, if you subtract the area of the triangle, you will get the area of the shaded region. So to find the area of the semicircle, you need the radius. And to find the radius, you need to use Pythagoras theorem. So Pythagoras theorem will give you the diameter RQ. Half of that is the radius. And to find the area of a semicircle, it is pi r square by 2 or half pi r square. So I've mentioned the right angle here. Then by Pythagoras theorem, we find the hypotenuse or the diameter RQ. The radius is half of that. Then the area of the semicircle is half of pi r square. R we just found. Area of the triangle is half base into height, half PQ into RP, half this one into this one, because the sides containing the right angle. The sides containing the right angle. So area of semicircle, area of triangle. The difference, 1 minus 2, will give you the area of the shaded region. If this is a circle, diameter, you take any point on the circle, supposing diameter PQ, and this is R. You take any point on the circumference, join P to R, Q to R. This angle is the angle subtended by the diameter at the point R on the circumference of the circle. And this angle is 90 degrees. Anywhere you take a point here, S, Join P to S, Q to S, 90 degrees. All right, children. Next one. So here we already know the formula to find the area of a circular ring. Okay, the area of this region. The area of this region. We have a formula to find the area of this region. Who can tell me? These are two concentric circles. I'm not talking about the figure given in the question. I'm asking with respect to the one I have drawn. In the figure I have drawn, I've shown two concentric circles. Two concentric circles. I want the formula to find the area of the shaded region.
Ma'am, area of the bigger circle minus area of the smaller circle.
Yeah, what's the formula to find the area of the bigger circle? Pi
R square, capital R square.
Minus pi.
Small r square.
Very good. So pi common, r square minus r square. So pi r square minus r square is the formula to find the area of a ring. Area of ring. Area of a ring is equal to pi capital R square minus small r square. Now, listen to this carefully. The area of this full thing, the shaded region is pi r square minus r square. The area of this full thing. The area of this full region is pi r square minus r square. Now, the region shaded in the question, is a portion of the full area, is some portion of the full area pi r square minus r square. Yes or no? See that? This is the shaded area. We need to find the area of this region. And this region is some part of the whole ring. Whole ring. This is the ring. The area between the two circles. This is the ring. This area is pi capital R square minus small r square. This area is pi capital R square minus small r square. This area. And the area shaded in this question, this one, this is the area shaded in the question. This one, that's all. This one is not shaded. This is not shaded. This one is not shaded. Shaded region is from here to here. Only this one is shaded. This is shaded. This one is shaded. The shaded region is some part or occupies some portion of the area of this full thing, which is pi r square minus r square. So you just have to fix a fraction to this full area. The full area is pi r square minus r square, and the shaded region occupies some part of this area. What part of that area? 40 by 360. 40 by 360. So theta by 360 into pi capital R square minus small r square will give you the area of any portion of the circular ring. If you want to find the area of any portion of the circular ring, you can find it using the formula theta by 360 into pi capital R square minus small r square. Am I clear, children? So the answer for this one is 40 by 360 into pi capital R square. It's given there, 14. So 14 square. Minus small r square, minus 7 square. This is the formula 40 by 360 pi capital R square minus small r square, and yes. All right, children. Okay. Please acknowledge Understood?
Yes, ma'am.
Yes.
Okay, Raja. What happened to
Yes, ma'am.
Prajit today? Prajit, are you there?
Yes, ma'am.
Okay. Okay. Arjun,
Yes, ma'am.
following?
Yes, ma'am.
Ranjan?
Yes, ma'am.
Okay. Did you watch the recording, Ranjan? Last class, you were there, but okay, you were there in the last class. Okay, fine. Are you following? Were you present throughout the last session, Ranjan?
No, ma'am. I will tell you the reason later.
All right, all right. Okay, okay. Okay, Danya. Danya, did you watch the recording, Danya? What about Florentina?
I understand.
Okay. Raja, did you have time to watch the recording?
Ma'am, I did not watch the recording, but I can understand with the three sums that you send in WhatsApp.
Oh,
Somewhat I
okay.
can understand the formulas and etc.
Very good. Okay, nice. All right. Danya, Florentina, Prajit, Sashank, Rakshit. All right. Rashmi, since you will not be able to communicate, I didn't ask you anything, Rashmi. You can later text me if you're following. All right. Yeah. I'll give you 2 minutes time. We need to find the area of the shaded region. The whole thing is shaded. Whatever you see, the entire thing is shaded. So think about it. Just give me a minute, children. I'll come back. Yeah, who wants to tell me? How do you find the area of the? Yeah.
I got 166.29.
No. I want the idea first. Tell me the idea in words.
Ma'am, first I found the area of the circle, and then the area of the major sector, and then the area of the triangle, ma'am.
Why did
And
you
then I
find the
got-
area of the circle? Why did you find the area of the circle?
Ma'am, I actually found the area of the circle and then subtracted the minor sector from it.
Okay.
Instead of directly finding the major sector, I did that by mistake.
Okay. Fine. Okay. Yeah, that's right. So the area of the shaded region, the whole thing is shaded. The area of the shaded will be, the area of the shaded region will be the area of the equilateral triangle. The area of the equilateral triangle, root 3 by 4a square. Root 3 by 4a square. Area of the equilateral triangle plus the area of the major sector. Major sector. See, you can see the two radii and an arc. You can see this is center, radius, radius. And you can see the arc. This one, this is the arc. And this is the major sector angle. I've told you the major sector angle will go in the same direction as the arc. This is the major arc. This one is the major arc. And this angle is the major sector angle. Since this is 60 degrees, this one will be 360 minus 60, 300 degrees. See, children, we have taken the formula like this. Area of the major sector is equal to 360 minus theta. If you can, 360 minus theta meaning 360 minus 60, not 360 minus 300. You have to take the respective sector angle. Supposing you take 300 directly, then you don't have to, it's not 360 minus 300. The major sector angle, what is the major sector angle? 300 degrees. So 300 degrees by 360 into pi r square. Okay, so this is the major sector angle. This is 60 degrees because equilateral triangle. So this one will be 360 minus 60, which is 300. This is 300. So area of the equilateral triangle, root 3 by 4a square, plus area of the major sector, 300 by 360 into pi r square, will give us the area of the shaded region. So see here, it's not a, it's not mandatory to write 360 minus theta. It's not mandatory. You can write like this also, reflex of whatever is the major sector angle. The major sector angle is the reflex angle, the reflex of angle AOB. This is angle AOB. This one is angle AOB. And this is the reflex of angle AOB. Reflex angle is an angle whose measure is more than 180 degrees but less than 360 degrees. A reflex angle is an angle whose measure is more than 180 degrees but less than 360 degrees. So you can write this also. Reflex of angle AOB divided by 360 into pi r square. So area of the equilateral triangle, area of the major sector, add both to get the area of the whole figure. Yeah. So in a circular table cover, okay, of radius 32 centimeters, a design is formed, leaving an equilateral triangle ABC in the middle, as shown in the figure. Find the area of the design. So this table cover is circular. There is a design, some design is formed like this, and the design leaves an empty equilateral triangle in the middle. Should find the area of the design. That means you must find the area of this region plus this region plus this region. In other words, you'll have to find the area of the circle minus the area of the triangle. Area of the design is area of the circle minus the area of the equilateral triangle. See, how to understand what is to be found goes like this. So the idea is area of the circle minus the area of the equilateral triangle will give us the area of the design. Okay, in that case, for the circle, you need the radius. Do you have? Yes, we have. Radius is 32. Then no problem. Any question related to the circle can be answered with just the radius. You just need the radius for a circle and we have it. Okay. Now for the triangle. To find the area of the triangle, you need to know the side of the triangle. Root 3 by 4 into side square. For an equilateral triangle, it's enough if you know the side. You can answer any question, but that's not known. We don't know the side of the equilateral triangle. So that is what you should find first. Before you can find the area of the design, you should first find the values you need for the figures in this whole figure. So for the circle, we have the radius. For the equilateral triangle, we don't have the length of the side. So we'll first find that. Then the area of the circle minus the area of the triangle. Okay. Yeah, just wait for some time. Just let me know how we can find the length of the side of the equilateral triangle. Oh. Yeah, I'm right here. Please read the question and tell me your idea. How do we find the length of the side of the equilateral triangle? Is a question.
Maybe trigonometric ratios.
Correct. Trigonometric ratios, right. Yeah, tell me. Go ahead. All right, we'll do it together. So we have some properties, regarding the in-center and the circumcenter. Okay, when we have an equilateral triangle like this inscribed in a circle. So let's see those properties first. Now, this is an equilateral triangle. And the circle which now you can see is the circle which runs through the vertices of the equilateral triangle. Equilateral triangle ABC, and you can see that the circle in this figure, the circle, it runs through the vertices A, B, and C. So clearly the circle acts as a circumcircle to the equilateral triangle ABC. A circle which runs through the vertices is a circumcircle. A circle that touches the sides. A circle that touches the sides of the triangle like this, which lies inside the triangle and which touches the sides of the triangle, is the incircle. And for an equilateral triangle, the incircle and the circumcircle, sorry, the incenter and the circumcenter coincide. The circumcenter is the center of the circumcircle. The incenter is the center of the incircle. Circle, center. Circle, center of the circle. If it is the circumcircle, the center is called the circumcenter. If it's the incircle, the center of the incircle is called the incenter. Incenter is for the incircle. Circumcenter for the circumcircle. Both represent the center of the respective circles. Now the property is, for an equilateral triangle, the incenter and the circumcenter will coincide. The incenter and the circumcenter will coincide. So for the equilateral triangle ABC, this one is the incenter. That is, it's the center of the incircle. Here there is no incircle. There is no incircle here. But there is one incircle for this triangle. So that the center of that incircle and the center of the circumcircle, which you can see here, it's the same. They'll coincide. And further, if you join the incenter to the vertex like this, OB will be the bisector of the angle B. These are properties. These usually form a part of the constructions of standard 6 and 7, which you don't have in CBSE syllabus. So you have to remember this theoretically. Otherwise, in the ICC syllabus, we have constructions. We have construction of incircle, circumcircle. So we see the properties through constructions. See, when you do something, like when you learn something through diagrams, through visuals, it's easy to understand and to remember also. Easy to understand and remember. So we don't have this in CBSE. So this becomes a part of the theoretical knowledge for you. So when you join the incenter to the vertex, or to when you join the incenter to any of the three vertices, now here we've joined O to B. Now OB will be the bisector of this angle. OB will be the bisector of this angle. So all this you don't have to write. This is the, like the flashback kind of, the background behind taking this as 30 degrees. We're going to take this angle as 30 degrees. So why is it 30 degrees? Okay, so this is the incenter. When you join the incenter to the vertex B, OB is the angular bisector of this angle B. And we know that angle B is 60 degrees because it's an equilateral triangle. And this is the bisector of the angle. So it will be 30 here and 30 here. And then we drop a perpendicular from the center to the chord. We know that a perpendicular from the center to the chord bisects the chord. We know that the perpendicular from the center to the chord bisects the chord. So now we have a triangle here. We have a triangle OBM. Now, to use trigonometric ratios, it is enough if you know one angle and one side. Any one angle in the right triangle and one side. If you have these two, Okay, let me put it like this. You just need to have two things, two pieces of information. So in a right triangle, when you know two things, you can find everybody. You can find everything else. In a right triangle, when you have two values, any two values, one angle, one side, or two sides, anything, you can find all the other details using trigonometry. In center, O, angle bisector, angle bisector, so 30 degrees. Drop a perpendicular from the center to the chord. That's a construction. Okay, you can draw a perpendicular from the center to the chord. 9th standard, we have seen this. So this is 90 degrees because that's a construction. We draw a perpendicular from the center to the chord. And we know that the perpendicular from the center to the chord bisects the chord. So M becomes the midpoint of the chord BC. M becomes the midpoint of the chord BC. Now in this triangle, we know one angle 30 degrees and we know that OB is 32 because radius. OB is 32. So now this is sufficient for us to find BM. And once you find BM, double it to get BC. And BC is the side of the equilateral triangle. So now what angle connects 30 degrees? You need to connect the angle with what you want to find and what you already have. You need to connect the angle with the known thing and the unknown thing. You need to connect the angle 30 degrees with the known thing OB and the unknown BM. BM you want to find, OB you know. Okay, so what is the relationship between this angle 30 degrees, BM and OB? BM is the adjacent side. Children, just a minute. Okay, so for 30 degrees, BM is the adjacent side and OB is the hypotenuse. Adjacent by hypotenuse, cos 30 degrees. Cos 30 degrees is equal to adjacent BM by hypotenuse OB. So the value of cos 30 degrees is √3/2 is equal to BM, we don't know, by 32. So BM is equal to 32 √3/2 to 16 √3. BM is equal to 16 √3. Now once you get BM, double it to get BC. BC will be 2 into 16 √3. So that is again 32 √3. So we got the side of the equilateral triangle. Now find the area of the triangle, area of the circle, subtract will get the area of the design. Now, children, coming from the beginning, the idea is easy. Area of the circle, you have the radius, so pi r square. You can find that easily. Area of the equilateral triangle, that also is easy, √3/4 squared. The thing is, we don't know the side. But once you find the side, you just have to find the area of the equilateral triangle and subtract area of the circle minus area of the triangle to get the area of the design. So the thing is, how do we find the side of the triangle? For that, we use trigonometry. That's all. For that, we use trigonometry. So O is the circumcenter as well as the incenter because ABC is an equilateral triangle. You can see the circumcircle and O is a circumcenter. You cannot see the incircle here. There is no incircle. That's why you can't see it. There is no incircle here. But if there were the incircle, this only will be the center of that circle also. So that means O is the circumcenter as well as the incenter. join OB. Then OB is the bisector of angle B. Angle B is 60 degrees. Then if it's bisected, 30 degrees. This is 30 degrees. 30 degrees. Drop a perpendicular from the center to the chord. The perpendicular from the center to the chord bisects the chord. So M is the midpoint of BC. Now we need to connect 30 degrees with what you want to find, BM, and what you already know, OB, which is 32. And that is cos 30 degrees. Find BM, double it, find BC, and you got the side. Yeah. This is one way of finding. You can also find the length of the side of the triangle using the property of chords. Equal chords subtend equal angles at the center. Equal chords subtend equal angles at the center. AB, BC, and AC are the sides of the triangle, but they are also three equal chords in the circle. Because equilateral triangle, so all the three sides are equal. And the three sides are also the chords of the circle. So the equal chords, then they will subtend equal angles at the center. So the angle subtended by every side meaning because every chord, so every side of the center will be equal. So this is the angle subtended by BC at the center. This is the angle subtended by AB at the center. And this is the angle subtended by AC at the center. So 360 divided by 3, 120, 120, 120, 120. So 120 degrees. Drop a perpendicular from the center to the chord. Drop a perpendicular from the center to the chord. So it bisects the chord. So this one is equal to this one. And now this angle is 120, no? Now when you drop the perpendicular, you have two triangles. These two triangles you can prove are congruent to each other. So it'll be 60 degrees here and 60 degrees here. 60 here, 60 here. Because these two triangles are congruent to each other. So now you know this angle is 60 degrees and you know this one is 32. So connect 60 degrees, 32 and this opposite side, BM. You get the same value. I repeat this one. Join OB and OC. Equal chords subtend equal angles at the center. So this is 120 degrees. Drop a perpendicular from the center to the chord. Now the two triangles are congruent to each other. So this angle will be 60. This will be 60. So this is 60. Now take this triangle. Take this triangle. This angle is 60 degrees. And this one is 32. You need to connect you need to connect 60 degrees, 32 and BM. So for this angle, it's the opposite and hypotenuse. So sine 60 degrees. Sine 60 degrees is equal to opposite by hypotenuse. So you can find BM, double and get BC. Yeah. So you should remember this idea. How to get that triangle, angle and all that. Got this, children? Yeah, I have done it both the ways, luckily. Okay. This one is 120. Okay. Oh, I've done it in a different way. Okay. I'll tell you that also. Yeah, this is that equal chords which I explained. Equal chords subtend equal angles at the center. Then we understood no, that these two triangles are congruent, so this will be 60. Then we find BM, double we find BC. Then the area of the design is area of the circle minus area of the equilateral triangle. So here what I've done is, the other thing is, you can also do it like this. Not a different method, but you can do it like this. So you can also find the area of the sector like this. You can find the area of the sector. You can find the area of the sector. Sector angle is 120 degrees. You can find the area of the sector. All right. And the area of this triangle. The area of this triangle will be r square sine theta by 2 cos theta by 2. And the area of the sector minus the area of the triangle will give you the area of this design. Multiply that by 3. You will get the area of the entire design. Equal chords subtend equal angles at the center. So this one is 120 degrees. Next, find the area of the sector. Find the area of the sector. 120 by 360 into pi r square. We'll get the area of the sector. From that, take away the area of the triangle. Area of the triangle will be r square sine theta by 2 cos theta by 2. You can find the area of the triangle. Sector minus triangle, you'll get the area of this design. This answer you multiply by 3 to find the area of the entire design. This idea is what you see here. You can see I found the area of the sector 120 by 360 into pi r square. Area of the sector. Then the area of the triangle BOC. Area of this triangle. Area of this triangle r square sine theta by 2 cos theta by 2. Then the area of the minor segment. Minor segment is this design. This one is 1 minus 2. Then the area of the design will be 3 into that answer. Is what is here. This one is that dropping perpendicular and that method. You need to remember these ideas, children, because maybe this question you can do it like in this way, but these ideas will be very useful in other situations. Okay. It's time, so. No, I think anything I start will take another 15 minutes. 1 minute. Yeah, I think this we can finish faster. Yes. In this figure, OACB is a quadrant of a circle. Quadrant meaning the sector angle is 90 degrees. Quadrant meaning the sector angle is 90 degrees. Quadrant is a quarter of a circle. Quadrant is a quarter of a circle. Circle, 1/4 of a circle. This one. This one is a quadrant. This one is a quadrant. Radius is 3.5. Radius is 3.5. Children, tell me which is the radius? Meaning, is OD the radius? Is OD the radius?
Yes, ma'am. No, ma'am. OA is the radius.
Yeah, OA. Because this is the arc. This is the arc. This is the arc. So A and B are the points on the arc. This is the center. OB is the radius. OA is the radius. And the radius is 3.5. So this is 3.5. This one is also 3.5. Radius is 3.5. And OD is 2. This one is 2. OD is 2. Find the area of the quadrant. How do you find the area of the quadrant? The sector, see, quadrant is a sector. Quadrant is a sector. It's a quarter of a circle. Then the angle is 90. See, this one is the segment. This one is a segment. This is the triangle. This is a sector. Quadrant is a sector with sector angle 90 degrees. So how do you find the area of the quadrant? 90 by 360 into pi r square, correct? Area of the quadrant will be 90 by 360 into pi r square. And how do you find the area of the triangle? The area of the triangle ODB, area of this triangle, half base into height, half into, this one is 3.5 and this one is 2, half into base into height. Then the area of the shaded region will be the area of the quadrant minus the area of the triangle. So area of the quadrant 90 by 360 into pi r square, area of the triangle, and the difference will be the area of the shaded region. Class, use the emoji, raise your hand. Rajat, very good. Madhumita, Krishmi, Danya, Raja, Rakshita, Ranjan, Sashank, Florentina. Shri Krishmi is there. Okay. All right. All right, children. So that's it for today's session. Thank you so much, children. Good night. You may leave the call.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
children. Good night. Thank you.
Yeah.
Thank you, children.
Ma'am?
Good night. Yes, Raju.
Ma'am, can you send the meeting